Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 10. This is Newton's second law of motion, force and acceleration. Let's revisit our big idea again. An object accelerates when a net force acts on it. We will be covering two learning objectives with this flip video. State and explain Newton's second law of motion, which is number 5. And number 6, cite and discuss the factors which affect the force of friction between surfaces. But first I want to take this opportunity to talk a little bit more about weight. We've spent some time with our last couple of labs talking about mass, but I want to spend a little bit of time discussing this thing called apparent weight. Now, we talked about a bathroom scale before. So what is weight? What does a bathroom scale measure? The weight force is identified as force sub G equals mg. So F sub G changes when G varies. On or near the surface of the Earth, however, G is approximately constant. If a bathroom scale supports you, it provides the only upward force on you. Then it reads your weight. But suppose you stood with 1 foot on the scale and 1 foot off. Or what if a friend pushed down on your shoulders or pushed up on your elbows? Then there would be other contact forces on you and the scale would not read your weight. Another example, what happens if you're standing on a scale in an elevator? As long as the elevator is in equilibrium, that is, at rest or moving at constant speed, the scale reads your weight. But if the elevator accelerates upward, then the scale reads a larger force. What does it feel like to be in an elevator like this? You feel heavier. The floor presses harder on your feet. On the other hand, if the acceleration is downward, then you feel lighter, and the scale reads less. The force exerted by the scale is called the apparent weight. Imagine that the cable holding the elevator breaks. The scale that you're on would accelerate with acceleration equals negative g. According to the solution to the first example problem, the scale would read 0. Your apparent weight would be 0. That is, you would be weightless. However, weightlessness doesn't mean your weight is 0, but that there are no contact forces pushing up on you. Weightlessness means that your apparent weight is 0. So back to Newton's second law of motion. Newton was first to realize that the acceleration produced when we move something depends not only on how hard we push or pull, but also on the object's mass. He came up with one of the most important rules of nature ever proposed, his second law of motion. Newton's second law describes a relationship among an object's mass, an object's acceleration, and the net force on an object. Newton's second law states that the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. This relationship can be written as an equation. Acceleration is in direct proportion to net force over mass. By using consistent units such as newtons, capital N for force, kilograms, small kg for mass, and meters per second squared, small m /s squared, for acceleration, we get the exact equation. Acceleration equals net force divided by mass. In the briefest form, where a is acceleration, F is net force, and m is mass, A equals F over m. The acceleration is equal to the net force divided by the mass. From this relationship, we see that doubling the net force acting on an object doubles its acceleration. Suppose instead that the mass is doubled, then acceleration will be halved. If both the net force and the mass are doubled, the acceleration will be unchanged. Now let's talk about friction. In learning objective number 6, cite and discuss the factors which affect the force of friction between surfaces. Friction is a force like any other force, and it affects motion. Friction acts on materials that are in contact with each other, and it always acts in a direction to oppose relative motion. When two solid objects come into contact, the friction is mainly due to irregularities in the two surfaces. When one object slides against another, it must either rise over the irregular bumps or else scrape them off. Either way requires force. The force of friction between the surfaces depends on the kinds of material in contact and how much the surfaces are pressed together. For example, rubber against concrete produces more friction than steel against steel. That's why concrete road dividers have replaced steel rails. The friction produced by a tire rubbing against the concrete is more effective in slowing the car than the friction produced by a steel car body sliding against a steel rail. There are two kinds of friction: static friction force and kinetic friction force. Push your hand across your desktop and feel the force called friction, opposing the motion. Friction is often minimized in solving force and motion problems, but in the real world, friction is everywhere. You need it to both start and stop a bike and a car. If you've ever walked on ice, you know how important friction is. Friction lets a pencil make a mark on paper and an eraser fix mistakes. Think about friction as you push a heavy crate across the floor. You give the crate a push, but it doesn't move. Newton's laws tell you it should move unless there is a second horizontal force on the crate, opposite in direction to your force and equal in size. That force is called the static friction force. It is exerted on one surface by the other when there is no relative motion between the two surfaces. The crate may be moving now, but friction is still acting because if you stop pushing, the crate then slows. The force that is acting is called the kinetic friction force. The kinetic friction force is the force exerted on one surface by the other when the surfaces are in relative motion. But friction is not restricted to solids sliding or tending to slide over one another. Friction also occurs in liquids and gases. Both liquids and gases are called fluids because they flow. Fluid friction occurs as an object pushes aside the fluid it is moving through. Have you ever tried running a 100-meter dash through waist, deep water? The friction of liquids is appreciable, even at low speeds. Air resistance is friction acting on something moving through air. Air resistance is a very common form of fluid friction. You usually don't notice air resistance when walking or jogging, but you do notice it at the higher speeds that occur when riding a bicycle or skiing downhill. When friction is present, an object may move with a constant velocity, even when an outside force is applied to it. In such a case, the friction force just balances the applied force. The net force is zero, so there is no acceleration. For example, a crate moves with a constant velocity when the force pushing it just balances the force of friction. A sack will also fall with a constant velocity once the force due to air resistance balances the sack's weight. And we draw this by showing all of the forces acting on an object in a free body diagram. Let's talk just a little bit about linking technology and talking about automobile designs. The first automobiles were little more than horse carriages with engines. Over time, engineers came to realize that by reducing the frontal surface of cars and eliminating parts that stick out, the air resistance force on a car could be reduced. When a car cruises at a constant speed, the net force on the car is zero. By lowering the air resistance force at any speed, the amount of force needed by the engine is reduced, meaning better fuel economy. Over the years, cars have gotten sleeker with teardrop-shaped bodies and teardrop shapes around side mirrors. Door handles are set into the doors. Even wheel wells and the undersides of cars have been smoothed. Automotive engineers use computers to design cars with less air resistance and use wind tunnels to measure the car's air resistance. Thank you.